So hello to everyone who's just started watching on the record. Okay, so the notebook I shared basically is a sort of a cheap rip-off version of the work that Kevin Yang and his colleagues are doing. There's a link somewhere in the description that I've put in the header of this to some of the work they're doing. It's a team of people at, I think it's mostly MIT. They're basically doing a bunch of QSARs on whatever SARS-CoV related data they can get their hands on in the hopes of discovering a potential therapeutic treatment for SARS-CoV-2, basically. If you didn't catch my presentation last week on a deep learning approach to antibiotic discovery, the author, one of the authors, Kevin Yang, and maybe some others who were involved in that or are involved in this new COVID-19 therapy discovery program. And basically, they're applying the same sorts of neural networks that they used to discover a new antibiotic earlier this year in a pretty interesting and famous paper. Applying the same techniques to try and discover a potential therapy for COVID-19. So the biggest data sets that are vaguely COVID-19 related in terms of screening are those from SARS-CoV-1. So it's genetically fairly similar, and it's in the same sorts of family. Oops. And after the initial outbreak, a bunch of screening campaigns began to try and identify potential drugs to be therapies against SARS-CoV-1. And a lot of the drug screening programs are directed at some of the proteases within the virus. So the proteases are pretty key for the entire thing to function. So they kind of represent a potential single point of failure within the whole viral genome. So here we have a schematic of the viral genome. There's open reading frame 1A and 1B. It's 1A and 1B because they sort of are the same reading frame in terms of they get transcribed as one unit via some funky ribosomal frame shift mechanism where the two frames aren't really sync.
Sorry.
What was that? Oh, okay. All right, Alex, how you doing? Anyways, so the way the virus replicates, or the way the virus at least generates its machinery, is it generates it all as one long polyprotein, which it then snips down into the individual proteins that do various functions, like replicate the RNA and stuff like that. Why is it expressed as one long polyprotein? I'm not exactly sure, but I think this is fairly common in viruses. So if I had to guess, I'd say it's an efficiency thing. There are two main proteases that break down these polyproteins into their individual subunits. There's MPro, which stands for main protease, and there's 3CL-Pro, which stands for 3CL-like protease. And I'll be damned if I know what 3CL is, or 3C. So that's the gist of the target. The target being 3CL-Pro. And luckily, over the years, there's been some pretty major drug screening campaigns against these, or against 3CL-Pro at least. I've embedded a little YouTube video in this Google Notebook. You have to bear with me. I don't know if it's happening for you, but I've got crazy lag. Here we go. So here's a little informative video about the Drug Repurposing Hub, which is not exactly related to the screening campaign that I've just been talking about, but it's a database of drugs that either made it through clinical trials or almost made it through clinical trials or made it to some stage of animal trials. Drugs that are fairly likely to be safe in humans, but didn't pass their trials for their particular purpose for whatever reason. And they can be repurposed if you discover that they have another unknown activity. And they're normally a good bet because they've passed so many stages of testing, which saves so much money for the drugs companies. And this is how the antibiotic discovery paper works pretty much. They made a model of what they would predict to be antibiotics based on a data set that they had in-house, and then they applied that model to make predictions of drugs from the Drug Repurposing Hub. And from those, they identified a couple of effective ones, brought them in-house, and then did further testing, which resulted in the discovery of this new antibiotic that hopefully will start to go through actual trials at some point. Okay, aim of the tutorial. So I think we've cloned a repository before from GitHub, which is a website that hosts a lot of code-based projects. So we'll recap that. I wanna show you the apply function in Pandas. Sorry about that. So the apply function in Pandas, there we go, is a really neat practical way to sort of apply a function to a whole column of a data frame. So in our case, we'll be generating molecular scaffolds for every smiles code in our data set. And it's a way to do this with no for loops and in a single line of code. So that's neat. We're going to do some visualization of the molecules using the built-in Pandas Tools module in RDKit, which is pretty useful. We're going to generate some features of each molecule that we can then plug into our machine learning model. Essentially, we want to generate like a table where for each molecule we have a couple of columns with features like calculated molecular weight, log P, and some other stuff like whether or not the molecule contains a particular fragment. Then we're going to introduce the amazing scikit-learn package, which really neatly wraps a lot of machine learning algorithms and makes them easy to use without being an expert. Basically, it's a really good place to start, and it's a pretty solid library. We're going to do some machine learning dirty work, like for example, balancing the data set. And hopefully, if we have time, we will train our model on the data set that we have, the SARS screening data set, and then apply that to the Drug Repurposing Hub data set that I mentioned earlier to see if we can identify within that therapeutics that will potentially have activity against our target, the SARS-CoV-1 PL3-like protease. I think, you know, the PL3 might be papain-like. Maybe I've made up the 3 as well. I'm not sure. Well, anyway, so the data that we're looking at is from a fluorescence energy transfer assay. If you want more data on it, then you can check out this link here, which will take you straight to the PubChem page for it. Essentially, it works by having 2 fluorophores that are close to each other. And when these fluorophores are close to each other, they can transfer energy to each other non-radiatively by dipole-dipole interactions. You'll notice that in this diagram we have 2 different color fluorophores. That's the protein that I've got here. That's supposed to be GFP. So the gist is, if they're very close together, like they are here, if they're linked by this peptide, we excite one with some photons, which won't naturally excite the other, but due to their proximity, say we excite the blue one, it will transfer energy to the yellow fluorophore, and then you'll get an emission of the yellow fluorescence if they're in proximity. The signal strength falls off very rapidly with distance between the 2 molecules. So if they sort of stray away from each other, then the signal from the second fluorophore pretty much disappears. So we can use that to detect whether or not two molecules are close to each other. And the way that's been used here is we're linking together these two fluorophores with a target site for the protease in question. That's pretty much how the assay works. If it's active, then it will cleave this peptide here. The molecules will drift away from each other, and we will no longer see the second fluorescence due to the fluorescence resonance energy transfer. The data was produced at the NIH Molecular Libraries Probe Production Centers Network. We have about 290,000 compounds in here, which is pretty cool. And the authors also state that there might be some assay artifacts in there, like, for example, dust in the microplate that might lead to false positives, false negatives, etc. And the data, fortunately, has been aggregated by this guy I mentioned earlier, Kevin Yang, who's a student at MIT and was one of the authors of this deep learning antibiotic discovery paper. And he's aggregated it into a really convenient data frame, or a CSV, that we can use. And here's a link to the project that I mentioned earlier, which contains a bunch of MIT scientists using AI to try and find cures for COVID-19, or therapeutics, small molecule therapeutics for COVID-19. So like an actual version of what I'm gonna show you today. I'm gonna show you the cheap rip-off version. And with that said and done, I'm going to get into it in my own notebook, which I'm going to call tutorial. Let's call it that. Okay, so the first thing I do in the Colab notebook is I visualize the protein in question, the target in question, the 3PL Pro. So I'm going to import Py3D-mol, which is a Python 3D molecular visualization package. If you don't already have that, you can install it using pip or conda. I think if you dig through the Colab notebook, there might be something in there. If you struggle with that, then put something on the group and I'll see if I can help you. Okay, I've written down what I'm supposed to put in this to actually render this molecule, because I'm not very familiar with this library, and most of the snippets that I use I've just stolen. So I define an object view equals Py3D-mol dot VIW, and I define a query. Query equals PDB, and the PDB code for this particular one is 6W9C. So there are quite a lot of structures available for the protease that I'm using, and the one that I chose is a homotrimer of 3 of these things in complex with each other. I chose that one because it was simplified. Some of the other ones were in complex with other proteins, which I couldn't be asked to sort of sift through. So it's returned it, or rendered it in a line structure, and I want to highlight one of these chains. So I'm going to access this view object, view dot, and there's a set style option, which I'm hoping I can find on autocomplete. But okay, so normally when I'm doing stuff in a Jupyter notebook, I'll use tab autocomplete on pretty much everything because I can't always remember what my functions are called. But in this case, it didn't work. Now the notation in this particular function is really weird because, or at least by Python standards, because I think it gets passed to a program in JavaScript. So the syntax is pretty different. But I define some curly brackets and say chain A to select chain A, and then in the next set of curly brackets after that, I define some styles for that chain, which I need to remember to spell right. I'm going to probably make quite a lot of typos during this tutorial, so please call me out if you see any of them. Cartoon.
Curly brackets in Python is a dictionary.
Yeah, that's true. Cartoon, and then okay, let's see how that goes.
Did you miss something out of cartoon?
Something's rendered. Cartoon color spectrum. Can you guys see that? In the Colab notebook, I figured out how to also add a van der Waals surface, but I'm going to skip that out today in the interest of time, because I think we could all use our time better than watching me sort of bumble through a package that I don't actually know how to use. But with this plotted now, let's move on to the data that we have. So I'm going to import pandas under the handle PD, because it's more practical. We'll remember that pandas is a tabular data handling library. And I'm going to define our data as pandas.readCSV, because it's in a CSV format. And relative to where I've started this notebook on my local machine, I think the path is ... which means up one directory, coronavirus data, tab autocomplete. Please help me out. Yes. plpro.csv. There we go. So you'll see that I actually made up the 3 in plpro. So it's not PL3 Pro, it's just PL Pro, which I think stands for papain-like protease, papain being the fruit, which has a particular protease, which I think is fairly well studied. Okay, so this is the data. It's only got 2 columns, the smiles and the activity. And we can only see the first 4 columns of it, but if we do the length of the data object, then we get 230 something thousand. So that's quite a lot. So it means that if we were to do a for loop to iterate over each row to do a particular task, it might take quite a long time. But let's have a look at how many hits that we have in the whole thing. Let's do some pandas commands. So to select the activity column, I'm going to use the shortcut to the locate command, which is pretty much just square brackets and the name of the column in question. Here we go. So each hit is a 1 and each miss is a 0. So to get the percentage hits, I'm going to call sum on that column, and it'll give me the sum of the hits, which isn't very much. And to get the percentage, I'm going to divide that by the total number of columns and times that by 100. Whoops. And I'm gonna save that as a variable called percentage hits. And I'm going to print that as a pretty F string. So print, I might have covered F strings before. F strings are a version of a string that you can print where you can pretty much drop in variables within the curly brackets. So let's do that. Percentage hits equals curly brackets, and I'll drop in the variable percentage hits. And then outside of the curly brackets, I'll put in the percentage sign, and you can see it prints it out in the middle of the string quite nicely. So if you want to print custom strings or have your program sort of print a different string each time or something like that, then F string is potentially a good way to go for you. Okay, let's look at some of the molecular scaffolds for the compounds involved. Now, scaffolds are the compounds once you've trimmed away all of the side chains, and it's a good way of grouping together compounds, especially in drug screening campaigns. You can say, or typically all compounds that are variants of a lead compound will share the same scaffold. And it's also a good measure of diversity of a data set. So let's import rdkit, which we'll remember is one of the cheminformatics modules. So from rdkit.chem, you know what? From rdkit import chem. Let's have a look at that, and let's also import its scaffold modules, specific programs or algorithms that will help us generate these scaffolds. From rdkit.chem.scaffolds, I'm using autocomplete here to try and find it. Import Merco scaffold. Awesome. Merco scaffold isn't a function itself. It's a module that contains several functions. So we can see if we dir Merco scaffold, it should list some of the functions within it. Get Merco scaffold from mole, get Merco scaffold smiles, get Merco scaffold smiles from smiles. That's the one I'm going to go for. So our function is going to be this, Merco scaffold from smiles. And let's paste in a smiles to see what it does. This one is complete. So you can see it's returned a smiles that's significantly shorter than what went in. And we can compare them if we want. Let's make an object called mole and call chem.mole from smiles. So I've included double quotes in there by accident. So I was hoping that it would automatically render in the cell underneath, but it hasn't. So I'm going to import from rdkit.chem import draw and call one of the draw functions on that molecule. Multi-image, let's try that. No. Okay. There we go. So the problem was I was using moles to image plural and I was giving it one, which it hated. Okay, so let's compare that to the scaffold that we've just generated, which is this. Okay, so, you know, that's quite long actually. I'm gonna Control Z myself out of that. I'll define a new variable down here called scaff, and that should return, and that should be the smiles of the scaffold of this. And then if we call this chem wall from smiles of the new smiles, and then draw that, and I'm gonna do the whole thing in one line because I feel like it. Mole from smiles. Okay, so there's a function that lets me draw it directly from the smiles, so I'm gonna try that. Oh no, what a disaster. Mole to image. Sorry about this, everybody. Chem mole from smiles. Here we go. Okay, so that only took ages, and here is the difference between the scaffold here and the original image, the original molecule up here. So you can see that the only things that the algorithm in question retains are the ring systems and the linkers between the rings. Everything else it considers as a side chain, and it crops them out. So that's pretty much the result that you get from the Merco scaffolds. I've left a link to the original paper in the Colab notebook if you're interested. And let's go back to our data. So I want to insert a new column to the right here, which contains scaffolds for every single molecule in the entire data set. So I'm going to define a new column and then set that column as the result of applying a function to every smiles in my data frame. I'm going to call the new column scaffolds equals, and now we're getting on to the apply function. So the apply function applies to a series or an individual column. So you can see here I've selected the smiles column from which I'm going to apply, and I'm just going to paste in my Merco scaffold from smiles function. Now, given that it has to do this about 230,000 times, I'm going to make a timer by importing the time module. Start equals time dot time. It's worth noting that the timer doesn't actually start at 0. It starts at whatever the system time is at that point. End is equal to time dot time. So that'll be the time after it's got through this apply operation. And then we can print, let's do another F string. Time taken is equal to end, which will be bigger than the start, minus start seconds, because it's measured in seconds. Okay. So in the Colab notebook, which probably runs on a computer that's much faster than my laptop, that took about 70 seconds or something like that. On this computer, I'm expecting it to take much longer. So whilst that's running, I think we can move on to some of the next cells. I'm going to refer back to the Colab notebook to see if there's anything I've missed or remind myself of what I'm supposed to do next. Okay, so I didn't actually cover cloning in my local notebook because I'd already cloned the repository. But in order to clone, you need the link to the page on GitHub. What is cloning? It is basically making a copy of the entire file system that they post up here into whatever directory you specify. And if you don't specify that directory, then it will be from wherever you ran the command from. So this is the repository that we're cloning. We can see that he's left a nice description of pretty much everything in there. We're full of links, which is awesome. And we can see there are folders, there are files, and there'll be files within the folders. So currently I'm using data from this data folder, and the PL Pro CSV that I'm using at the moment is right here. It's not rendering here, but we can look at the raw version of it via this link. And here we go. There's a raw CSV file. We'll remember that CSV stands for comma separated values. And if you don't render it into a table, this is what it looks like. We have the column headers up here separated by commas. And then we have smiles and the numbers at the end. I'm going to close that down. The command I've done, I've just got a warning from Zoom saying my high CPU usage is affecting the meeting quality. Am I breaking up for anybody?
Look okay to me.
Okay to you. Okay, that's fine.
Actually, to me.
Cool. Okay, underneath the git clone command, I've installed a program called tree, which is a simple command line program that lets you draw a tree structure of a file system, which is exactly what I've done here. I've had it draw a structure of the directories, which is the -D option, of the coronavirus data folder. And then it recursively goes through and shows me everything inside. This box here, we'll remember from last time we had to install RDKit, is the set of commands that you have to do in order to install Anaconda on Colab, which it doesn't come with naturally, and then install RDKit. So those are those. And then we have pretty much where I'm up to here. So we can see in the Colab notebook, it took 75 seconds, and for me, it took 172 seconds. All right. Did I remind myself of what I was supposed to be doing? No. I'm going to go ahead anyway. So let's look at the data now, and we can see that it now has a new column called scaffolds. Let's have a little look at how many of each scaffold there are in there by selecting the scaffolds column, scaffolds, and calling the function value count. Series has no, yeah. Let's see what I put in the other one, because I swear it was a similar function. Yeah, okay, value counts with an S on the end. Here we go, and it's returned a single column, a series object, where the index is the smiles of each scaffold, and the values in the column are the number of occurrences of each one. So I'm going to make this into a new object called scaff counts. That should do. And I think it would be easier for me if these smiles codes weren't in the index but had their own column. So to do that, I'm going to do reset index, which well, I'll run it and then explain what it does. So what it's done is it's moved what was the index column, these smiles, into its own column, and then moved a fresh index that goes up in ascending order into the now empty index. The issue is that the column names are wrong now. So I'm going to rename them by accessing scaffcounts.columns. Did I spell that right? Nope. And I'm going to give that a list of what I want to rename the columns to. Smiles, scaffold smiles, so I don't get confused later, because I know that's going to happen. And count. That should do me. Okay. And there we go. You can see the names have updated, and it looks vaguely sensible. I'm going to plot a histogram of the amounts of occurrence of each scaffold. I won't be able to identify which scaffold is which within the histogram, but it'll give me an idea of the distributions that we're looking at, because it can be pretty difficult to see from just this. So let's import our favorite plotting library, matplotlib.pyplot. There we go. And let's install that as, import that as PLT, which is a handy shortcut. The histogram function in pyplot is plt.hist, and then you pass it a set of numbers, basically. So the set of numbers we're going to pass it is the counts column from scaff counts. So let's do that now. And we'll call the plt.show to make it actually show the histogram. Uh-oh. Okay, so it doesn't like what I've called the column. Probably because I spelt it wrong. Here we go. Okay, well, that's really uninformative. So let's make some changes to that. Let's change the number of bins that this data set is divided up into. So let's call bins equals 100. How about that? And let's make it wider. So I'm going to call plt.figure to change the default canvas size parameters. And within that, fig size equals 15 and 5. That should make it wider. Okay, we're getting better, but it's still not that useful. Let's call, let's change the y-axis to a log scale. That would be useful. plt.yscale, and I'll pass it the string log. Here we go. Okay, that's more useful. So we can see somewhere over here there is a scaffold that's appearing just shy of 7,000 times, and we can see from up here that that's the benzene scaffold, and there's plenty of scaffolds that occur just once. I haven't actually labeled off any of the axes, so let's remind ourselves how to do that. plt.xlabel to access the x-axis label name, and what am I showing here? Counts in screening dataset. So this is a bit of a confusing histogram because I'm counting how many counts there are, but yeah, just let's bear with me for this one, or even better, skip on to something else. So the purpose of having this histogram was because I wanted to draw a cutoff to remove outliers from the data set to make it a little bit easier to make my model. So basically I wanted to remove compounds that only occur once in the data set. Or sorry, compounds whose scaffold only occurs once in the data set. So let's go back to our data and do that now. Before I do that, actually, I was meaning to show you Pandas Tools in our dkit, which is actually a pretty useful and neat function. So let's do that now. From rdkit.chem, import Pandas Tools with capital T. Pandas Tools will let us render some of these molecules in our Jupyter notebook, which is pretty handy. Let's go for scaff counts. So Pandas Tools contains this function called add molecule to data frame, or add molecule column to frame. And one of the arguments that you give it is the data frame in question. And it's worth noting that it updates the data frame in place, so you don't need to say data frame equals and then this function. It will handle everything for you and update scaff counts in this case. Okay, what else do I need to pass it? The smiles col equals, and then the name of the smiles column, smiles in this case. And optionally, the name of the column which it will create that will contain the molecules and the renderings of the molecules, molcol equals, and I'll just have that called moles. Okay, well, what a disaster. What have I done wrong here? Smiles. Yeah, that will be because once again I have accessed the wrong column. So scaffold smiles is what I should have been accessing. One of the discrepancies between Colab and Jupyter Notebook when it comes to Pandas Tools is that in a local Jupyter Notebook, you have to generate an HTML of this Pandas data frame in order to have it actually render the molecules. So briefly, I'm going to do that now. Yeah, you can see in this new moles call, it has an HTML link to where the molecule should be. So let's have it render that link from ipython.display import HTML. Okay. We're almost out of the woods. So Pandas data frames have a function called toHTML. So I'm going to call that on this data frame. And given that the Pandas Tools add molecule to data frame function took a few seconds to run on my computer, I'm just going to comment that out because it's already done, so it shouldn't make a difference, I'd hope. But we'll see. So what does this do? This generates an HTML object for the data frame, which will be a bunch of garbled looking code when it comes out the bottom. So to have it actually render nicely, I call HTML on said data frame. And when my computer finishes working, it should render nicely below. I'd hope that'll be quicker for you guys because I've got a particularly slow laptop, but you know, we'll see. So that was a little tangent that I made from the true objective, which was it was to filter out molecules whose scaffold occurs only once in the data set. So I won't be able to show the data at the moment because it's still running the cell before, but we can have a little look at what it did have. We know that it has a column called scaffolds, which I define up here. There we go, data scaffolds. Yeah, sure taking its time. Okay, so how am I going to filter this? I want to have some rules where, well, I'll use this scaff counts. So how about scaff counts? Let's update that or let's make a new object called scaffolds to use equals scaff counts, and let's do a lookup function or a locate function by scaff counts where the count of the scaffolds is greater than 1. Okay. I'm going to press this interrupt the kernel because I have lost a little bit of faith of my HTML rendering, but for to see what it looks like, then just refer to the Colab notebook where it should have worked. Okay. So what? Let me break down what I've done here. Yeah. So the core of this lookup function is this little logical test I have here. So let me put that in a cell below to show you what's going on. Scaffold counts where the column count is greater than 1. You can see that returns a lot of trues and falses. And I can use that to look up values from the original scaffold counts data frame. This only works if the length of the column returned in the logic test is the same as what you're locating from. For example, if I were to do a logic test on a short data frame and then apply that to a long one, the computer would throw an error. Okay, scaffolds to use is the variable I've defined here. Scaff counts.lock, scaff counts greater than 1. So I can find just the scaffolds by narrowing it down to this particular column, and I want to locate the original data set by going data, now what one column's called? Scaffolds. I'm going to use this function called isIn, which is pretty useful for doing lookups like this as well. And in this case, it doesn't matter that the lengths of what I'm comparing are different, but basically what I want to do here is take all of these scaffolds from the original data set and only return ones that are in the scaffolds to use variable, which remember is where scaffolds occur more than once. So let me copy this column into the function, and we can see that again it returns trues and falses and so on. And just like before, I can put that within some square brackets and locate by that data.loc. And here we go. We have a significantly shorter data set at 192,000, but it's still quite a lot. So I'm going to set this as a new variable, and let's call it imaginatively data2. Why not? Okay. I'm going to remind myself what else I need to do. I think next we had some feature generation. Here's an example of what the Pandas Tools molecule data frame should look like if it actually renders, but for some reason on my computer it wouldn't.